Guys, hope all of us are doing great. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. I'd like to welcome each and every one of us to our discussion for today. I'm going to look at an additional concept on the concept of charging and discharging of our capacitors. Now, in our last discussion, I had mentioned basically that we're going to use an RC circuit, which is a resistor-capacitor circuit, which we had said is going to assist us in trying to evaluate the amount of charge or discharge, the amount of current and voltage or the potential which is going to be involved in this specific aspect of a charge. And thereafter, we had said that as well we can evaluate the charge which is going to be involved in this particular case. Now, we had listed a few examples of how we can perhaps give this one in terms of equations. And we had said that basically this specific circuit is going to work in a way that when this particular switch is closed, the current is going to flow in the clockwise direction, and therefore this is going to lead to accumulation of charges at the positive and negative plates of this specific capacitor in this particular circuit. Now we're going to see that after these ones have accumulated, the current is going to be gradually decreasing to a point whereby it's going to be particularly stopping, and therefore we're going to have the current dropping to zero when this specific capacitor is fully charged. Now we had said that we can give this particular charge or the final charge of this specific capacitor using this initial for Q sub F, and this of course is going to be assisting us interpret the second part of that specific graph. Now we had mentioned basically that the voltage across this specific resistor can be given in terms of V sub R. So this is going to be voltage across the resistor, and then we had said that we can give VC in terms of the voltage. So this is going to be the voltage across the capacitor, given those two specific illustrations for this one and this one. So thereafter we said that we can develop a relationship between the amount of or the potential which is going to be realized in this specific instance for this particular circuit. So we said that we can give the total potential as E equivalent to VR plus VC. So I mentioned the concept of Kirchhoff's law, which we're going to look at later, especially in trying to evaluate the connection of perhaps resistors and capacitors in series and parallel in that specific case. But I'm just going to give this one in terms of this particular equation, hoping that we can understand that one from that specific perspective. So we're going to have E in this specific circuit represented as a sum of VR, the voltage across the resistor, and the voltage across the capacitor given as such. And further, we said we can represent this one as E equivalent to IR plus VC. Now in this case, we had said that this specific point whereby the capacitor is going to be fully charged, that is going to be a point whereby this specific current is going to drop to zero, as we said. And therefore, for our equation which we have given us this, we can rewrite it in order to find the amount of current which can be represented. So making this one I the subject of the formula. So I'm going to give this one in terms of that one. So making that one the subject of the formula, that's going to give us VC over R, E minus VC over R. And this one implies that we can have still current represented as E over R minus VC over R. But we said that at QF, which whenever the time when the final charge, when the current has or the charge has fully accumulated, the current will be zero, and therefore the VC basically is going to be having a zero value at this specific point, which is going to be the current at this specific final part, and therefore we're going to have this one given as E over R. But we had stated that for us to represent this specific currents in terms of either instantaneous or the current as the instance at which this specific switch is closed, we're going to involve the aspect of calculus, which of course is going to give us an evaluation resulting to this particular formula. So we had said that this is going to give us I, which is going to be instantaneous current is equivalent to the current at the time when the switch is closed, which is I naught. And then we had said this is going to be multiplied as a negative value of that specific exponent and t over c given as such. So we had given a specific name for this specific combination of RC, whereby we referred to this one as a time constant. Maybe I can just give it. So this is going to be a time constant given as that, and this is going to be the denominator of this specific exponent which we had given in terms of RC, and of course that's going to be the time which is going to determine basically the time at which the capacitor is going to be fully charged. And therefore we said that this is going to assist us to measure how fast a capacitor can be measured, especially using this specific aspect of the exponent for RC and T. So in this case we had illustrated various of course representation, or the two specific representation for the concept of current against time. And of course this was basically this curve of this specific equation. So we had this one given as such. So at the beginning, whereby we're going to have I naught, this is going to be maximum current, where this specific switch is going to be switched on. And as time goes by, we're going to see that the current is going to drop perhaps from T2 for the T1. So this is going to be, let's give this one as 2I the T1, and then we're going to have perhaps I at the T2. So this is going to show that the graph is going to gradually decay as time goes by, and therefore we're going to have a zero current at the final part of it. But from our charting, we said that we can have this specific graph for the charge, which is going to accumulate up to QF, which is the final charge. And as we are going to see, as time goes by from T, perhaps 2T, and then 3T, the charge is going to accumulate to the maximum given as such. So I wanted us to have an additional part of the relationship between a current and charge. And of course, this is going to assist us in trying to find ways of evaluating some of the problem sets which we may come across relating to this specific aspect of charging and discharging of capacitors. So we can represent what we refer to as instantaneous charge and current using this specific formula as well. So just like current given for I naught, using that specific I, instantaneous current is equivalent to I naught e to the exponent of negative t over RC. This is going to be given as the charge Q is equivalent to Q naught A negative t over RC. So this is going to be analogous version of the first equation we had given, but this is going to be pertaining to the concept of a charge. And we had said that current basically can be given if we can be able to pinpoint the relationship between the two. So this is going to be given as E t over RC given as such. And these are going to give us the relationship between the two. So in other fashions, perhaps we are going to come across this specific representation, negative Q naught all over RC, and then we're going to have E and negative T over RC given as such. And this, of course, is going to present another version of this particular case, whereby this specific sign, which is a negative sign, is going to show that upon discharge, this is going to be a current that is going to flow in the negative direction as indicated by this specific sign for negative, which I've given at this particular point. So this is going to create clarity for us from the first discussion we had on the concept of charging, whereby we had given on current, the equation for current and this specific case, and therefore I liked our members to take note of this specific equation which I've given on the board for the concept of instantaneous current given as such. So kindly check our description box for various links of other videos, and also ring that notification bell and subscribe to our channel to be getting more updates in various discussions in mathematics and sciences. So that is it for now, guys. By God bless. We'll catch us in our next video.